recording here. Okay, so let's finish off. There was just one main thing that I wanted to kind of include before we wrap up. I don't, well, okay, fine. For review, we said that if I have the log of a times b, that's going to be the same, and how you can break them apart is by addition of the log of a times or plus the log of b. You can move back and forth between those, and that's going to be really handy when you're solving problems, right? If you've got something inside the log and you want to get it on its own, then one way to do that is to break it out into addition. Or similarly, if you're adding logs and you want to group them together, then you multiply them inside. And the log of a over b is the log of a minus the log of b. Oops, that doesn't look like a b. There. So those are the rules that we introduced last day. But I'll call that the end of the review. The only thing that I've kind of avoided talking about is the graph of the log. But using Desmos, we can have a look here. And how about a function? Let's take log base 10 of x. Oh, look at me, I'm all zoomed in here. What it's going to look like is like this. Okay. I'll bring this in. Crop it up. Hey, there. So one of the key things that we're going to notice is that there is a vertical asymptote at x equals 0. So it never touches x equals 0. It just goes on and on and on. And so we never get to 0. So every value of x that's just a smidge greater than 0 is allowed. So it's in the domain. And so what this shows us is that the domain of the log of any base of x is x greater than 0. In words, what that means is that you can't take the log of 0 or a negative number, right? And so here, therefore, we can't take the log, and I mean any log base, so I'll just write log base b. Okay? We can't take the log of 0 nor a negative number. The reason I mention that is because sometimes we're going to have to use the quadratic equation to solve for values of x that are inside the logs. So I've got an example. And what we need to check is that we're not taking the log of a negative number. And you can try it. You can do the log of 0 on your calculator, and it'll say, oh, no thanks, because it can't do it. And so you can try to take the log of a negative number. Hopefully it's saying no thanks. Good. So you can take the log of a negative number, and again, it's going to say, oh, no, I won't do that. And so another kind of fun fact is that the log of 1 is 0, right? If we think about it, if we think about the relationship between exponents and logs, right, which is that if I have the log base b of x is equal to a, right? If x is 1, okay, So here, if x is 1, b to the power of a has to equal 1, right? But in order to get to 1, if b is a positive value, which was one of the things that we established, then a has to be 0, right? Anything to the power of 0 is 1. Okay? And so here we get that a must be 0. So that's always going to be a fact. Any graph of the log is going to go through 1, 0, right? When x is 1, the output is 0. Okay? So that's nice.
And some examples from where like the main graph would always go through 0. The shape.
Yeah. Do you mean this one?
Yeah, that one.
The exponential function looks like that. 0, 1, 0. Feels like a special case. Off the top of my head, blanking. It would be some sort of exponential function if it looks like, if it's like this, but on the flip side, it's the exponential function. Let me just confirm it.
One of those ones that had 4 different graphs, and you had to figure out how it's transformed, I guess. Yeah, that's it.
Yeah, there we go. I don't know why I was doubting myself there. And then we can manipulate the exponential function, move it around. Same thing with the log, right? We can manipulate the log, but we're going to parking lot that until after the test. But just because it came up in one of the questions on the last assignment on 4.4, so that's why I wanted to talk about the domain of logs. Okay. Let's see an example here.
4.4 is part of the midterm.
Yes. Where's it? Oh. Nice and slow today. Okay, so that's the one that we did. How about we do this one? So if I want to solve this, I want to solve for x. We've got x's locked inside the logs. We know how to deal with that. I can raise it to the power of something, and usually I choose a convenient power, right, so that I can cancel the log base 10. So what I would do is I would take 10 to the power of the log base 10, and then they would cancel, and this x would drop down, and this x would drop down, or the x plus 3 would drop down, as long as I do it to the right-hand side as well. That's the one I forget sometimes, so it's normal. But it's bad. One of the things that we could do before we do that, right, I could take 10 to the power of all of this, but it's kind of messy. So what I'm going to do instead is I'm going to combine these logs before I go ahead, and then I only have one log to deal with. So here, I'm going to rewrite this as I'm adding the logs. So it's going to be log base 10 of x times x plus 3 is equal to 1. Now, our move to shake out something inside the log is to raise it to the same base. And so here, this is base 10, so I'm going to do 10 to the power of log times x plus 3. Or you can expand that out already if you want. I'll just keep it there to emphasize for a little bit longer. This 10 to the power of log base 10, they cancel. So then I'm dropped down x times x plus 3 is 10 to the power of 1. I'm just going to write it as 10. But it's just 10. So this is why we do what we do here, because this is log base 10, right? B to the power of log base b of x is x. Okay, so now we're back in familiar territory, right? If I want to solve for x here, then I've got x squared plus 3x is equal to 10. I can move everything over and set it equal to 0 and use the quadratic equation. X squared plus 3x minus 10 is equal to 0. Now this is a quadratic, which we know is going to have two solutions, right? Two values of x. And usually what happens is if it's inside a log, only one of those is going to apply, right? Because the other one is going to yield negative values inside the log. Spoiler alert, I guess. Oh, so quick. Yeah, you'd have to check. Yeah, -5 doesn't work here, doesn't work here. 2 works here and 2 works here. Nice. I'll write it out for completeness. X is -b plus minus the square root of b squared minus 4ac divided by 2a. I haven't even checked to see if I can figure out what adds to 3 and multiplies to -10. I don't even bother because I'm not good at it. Maybe because I refuse to practice.
I just started doing it and it's so fast.
If you've got the gift, but I don't. So I just use the quadratic formula always. 3 squared minus 4 times 1 times -10. Square root of 49 is 7, right? -3 plus minus 7 divided by 2. -3 minus 7 is -10 divided by 2, -5. And -3 plus 7 is 4 divided by 2. You did it. But it's all fun work. That's fair. You have to get to know it. And it is on your formula sheet, so. Let's see here. Let's put these into log of x plus, we had the log of x plus the log of x plus 3 is equal to 1. And if we take -5 in here, x can't be -5, right? We check, x can be 2. So therefore, x equals 2 is the solution. Okay. Any questions about that one? I am going to put one of those on the test because it brings it back to the quadratics and it's just like a nice, well-rounded question. But because I just talked about it today, I won't, if you just get to x equals -5 and x equals 2, I'm okay with that, right? You don't have to tell me that one doesn't work. Although, if you remember, that's great. Oh, I think I grabbed the wrong. Oh, well, that's okay. We can skip to this one. A word problem. Town A's population is currently 1,000, growing at a continuous rate. So that's one of those kind of trigger words. Yeah. So we've got, so the continuous rate of growth looks like f of x is a times e to the x kx. Is that how we usually write it? Where k is the rate. Could use t if we wanted because it's in years, but or f of t is a e to the kt. And this is for continuous. Town B's population is currently 5,000, but is dropping. Uh-oh. So it's decreasing at an annual rate of 5% each year. So now that's not continuous. That's just a regular rate, right? And so here, what color? I'll do Town B in green, and I'll do Town A in blue. So we have f of x is a times 1 plus r to the power of t, or in terms of t, because we have time as our variable here, same deal, a times 1 plus r to the power, oops, I see I did t already here. Bad, Emily, bad. So what we want to do is we want to figure out, well, f of t, or we could even use p of t for the population at some time point t. Sure, let's get fancy. P of t, P of t, right? The population at time t. So let's figure out what the blue P of t is. They have a population of 1,000, and it's growing at a rate of 0.06 t. And then we have Town B, which is starting with a population of 5,000, and then the rate is negative, right? Negative 0.05, because it's decreasing at a rate of 5% each year. And so then I have 1 minus 0.05 to the power of t. Huh? Yeah, right? Did I mix those up? No, looks okay. Okay, nice. They're so similar. Okay, so what do we want to do? We want to set these equal to each other. At what t are they equal? At what? So then I'm gonna have, put it on a fresh page here, 1,000 e to the 0.06 t. When's it equal to 5,000 times 0.95 to the power of t? There are a few ways that you can go about solving this, right? Regardless, at some point, you're gonna have to take the log because you wanna bring that t down from the exponent on both sides. The first thing that you could do is you could bring the exponents over to one side and then everything non-exponent t to the other side. That's an option. Or when you take the log of both sides, right, it'll drop the t down. Which one do you think you prefer? Let's take the log of both sides just as is. Right. I am going to use a natural log. so that I don't have to deal with this e anymore. Huh? So, but you can choose any log that you'd like. The log of 1000 e to the 0.06 t is the log of 5000. I just realized I'm saying it. The natural log there. Happy?
Just use base 10 and you'll never work.
I know it's strategic though,
Yeah.
but then I have to say common log. So now what I'm gonna do is I'm gonna split these up using those log laws, right? I'm multiplying inside, which means I can split these up and get this e to the 0.06 t on its own and 0.095 to the power of t. I can get it on its own. So then I'm gonna have the log of 1000 plus the natural log of e to the 0.06 t is the natural log of 5000 plus the natural log of 0.95 to the power of t. The problem is you aren't able to bring this t down or the exponent down until it's just the exponent on its own.
You start just bringing the 1000 over and then taking the ln, and then that just turns into 1.
Yeah,
That sounds
you can.
fascinating.
There's lots of ways that you can do it. I chose the longest way so that
Looks so good.
yeah, you're gonna kind of run into the same maneuvers regardless, but yeah, there's lots of other ways. I'll make a note even. There are many ways to solve. Enjoy. What I'm gonna do is I am going to simplify a little bit. I'm going to move this log 1000 over to the right hand side, kind of lump it with the log of 5000. I'm also going to drop this down, right? The natural log of e to the power of 0.06 t is just 0.06 t. Okay. So this becomes 0.06 t. Should I keep? Okay, fine. I'll keep it here for just a little bit longer. Now I can bring this t downstairs. The natural log of 0.95 doesn't go anywhere, but it's just a number. So now I've got t's that I'm gonna collect like terms. And so now I'm gonna do my mega move. I'm gonna do 0.06 t minus t times the natural log of 0.95, right? Collecting all my t's to the left. And then I have the natural log of 5000 minus the natural log of 1000. Pulling out that common t, I get 0.06, t times 0.06 minus the log of 0.95 is, what's this going to simplify to? Even if we don't take the logs out, you can if you want, but this is the same as the log of 5000 divided by 1000, right? Sneaky. There, I did it. I did it without writing down the step. All right. But I will draw that. So now if I want to solve for t, well, 0.06 minus the natural log of 0.95 is just the number, right? This is the exact value. And so now if I want t That's the natural log of 5 divided by 0.06 minus the natural log of 0.95. And that's the exact value, but that's hard to report to a boss or something. So they don't like that. You can try, but they don't like it. So just use your calculator. Log of 5 divided by 0.06 minus the natural log of 0.95. I get T is roughly 14.46122.986 years. Or some 14.46 years. That's when those populations will be the same. As long as you get to here, then you did it, right? So there's lots of ways that you could have picked this apart. Oh, it's not. Oh, come on. Pick this apart beforehand, right? You could have lumped together your powers of T and gone that route, but I don't think it's that bad. But you can play around. As long as you get to this T, then you're fine. Okay. Now, are you ready to make this test for me? Let's see here. So I posted those core concepts of these, and I'm going to bring it in to Notability. We're going to choose 20, taking requests. I've got a couple of right? Oh, where did I put that? Oh, shoot. Oh, it didn't go anywhere. Notability, create new note. Yes, done. There we go. So we're going to choose 20 concepts. There are a few kind of must-haves, but I obviously can't test you on all these things. So what are the must-haves? Well, 3.4, long division of polynomials to find the quotient and remainder. That's a must-have because that's the only thing we did in 3.4. So what's another one? And all I did here was I just put names to all the assignment questions, right? They can all be lumped into these categories. And so that's all I did. So this is from 3.1 assignment, 3.2 assignment. So if you want more questions from there, then that's where they are. And that's where I'm grabbing them from too. All right. Let's hear it. And
two from each then?
Whatever you'd like. Well, you said you liked these ones. Let's start from the most recent. Let's see here. Solve for x in the exponent. Solve for x inside the logs. Yeah, right?
exponential function passes through two coordinates. That's kind of fun.
There we go. Okay, where's that one? This one? I was gonna do that anyways, so it's nice to lay it out there, right? Oh, maybe not the graph. No, I wanted. Okay, this one, that's not the one I was thinking of. I want to find the equation given the point that it passes through.
Question 4.3, I think that
Uh,
Yeah, you get two coordinates and you have to figure out what it is.
yeah, right?
you're multiplying the exponent, right? When you put that point, it was always like 0 and 1.
Yeah. So I think that one is, so these ones?
Yeah, that's what it was. That was your point.
Yeah. Okay, you know what? Let's do this one. Why not? I'll give you a graph. Look at where it passes through 0a and 1ab, and then you can construct your exponential equation. Let's do that. Oh, here. This is the one that I was going to do. Construct an exponential function that passes through two given points, and then use it to solve a problem. Right? Then it has to say it follows an exponential curve or something like that. Compound interest, anyone? Throw it on there. I'll give you the equation, obviously. No, not explicitly. I can't remember. This formula sheet is outdated a little bit, but let's see here. Yeah, I'll give you those equations then. It's okay. How about these rational functions? Find the domain, the intercepts, and the vertical asymptotes. I'm not going to test you on the horizontal ones because that's, you're just looking at the powers in the numerator and the denominator, and then you figure out if it's 0 or nothing or a over b. But yeah, yeah. How about we throw this one on there too? Yeah, we have to do it. It's all we did in 3.4, but I'll just have one on there. How about given a rational function in factored form, classify the discontinuities as a whole or a vertical asymptote, right? If they are in factored form, then you can see if they cancel. If they cancel, it's a whole. If they don't cancel, it's a vertical asymptote. Please say fun.
Yes. So fun.
Where's that the ball thrown in the air? Did you guys like that one?
Physics.
Oh yeah, this one, solve word problems given the quad, so I would give you the quadratic equation just like they do in those assignment problems, right? The rocket launch or the ball thrown in the air.
How far out?
Yeah, and then at what time, how long does it take for it to reach the top and then the ground, those ones? Mm-hmm. Or do you want to go level up? From a word problem, build a quadratic equation. Yeah, exactly. Box, wire, ticket sales, whatever are those examples. How about, we'll only do one of these. Which one do you want?
Probably solve one.
This one, where I give you the equation and you don't have to make the equation. To me, they're relatively equivalent. Go easy on you. Yeah. Well, this one, I feel like it's not really an under pressure type of question. You have to have time to think about it and sketch it out. And whereas this one, I can just get you to jump in and do it. I would like to have one of these. Given the vertex, write it in standard form. Standard form is ax squared plus bx plus c. Right? So you've got that vertex form and the standard form, which is, and this is where you'd need to get comfortable with your formula sheet, is sort of on here a little bit. It's inside the completing the square bit for part 3 of the polynomial formulae. Yeah. How about one of these? If I give it to you, oh no, that's the same thing. It's basically the same thing, right? If it's in standard form, write it in the transformation vertex form. Or if I give you a vertex, write the quadratic. I guess we can choose between these two. Do you like going to standard form or going to transformation form? Oof, it's been a while.
Probably where it is now.
Where it is now? Yeah, I think so. How about given a quadratic in standard form? No. We can save that one for the final. It's feeling like kind of a hard test at this point. We'll throw in a long run and the degree of the polynomial. How about? Just for some easy ones. How many do we have now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, I was gonna do 20. I was expecting you guys to pick easier ones.
Yeah, I really like easy stuff.
How about we go back to the exponents and logs?
Like just shifting stuff into exponential log, it's super easy.
There. We're 14 just like that. How about yeah, this one I would probably smush those together and have an easy one and a harder one. So I'm okay with that. How about this generic one? Just evaluate expressions involving exponents and logs. It's generic. I like those. Was it this one or the other one? Oh yeah, no, this one. Yeah, so you get a huge log and you have to zip it up into one log. Nice. How many is that? 15? Well, let's see how what the distribution looks like. Is there anything from, yeah. Let's do something from 3.3. One thing, factor a polynomial to find intercepts. Ugh. Long run behavior of a factored polynomial. That might be fun. Polynomial inequalities can be kind of long. Find an equation of a polynomial with given qualities. That's those like it passes through this point and whatever. How about the long run behavior? That's important. How about we throw in the domain of a function involving a quadratic equation? Oh. Where are we at now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Where are we looking a little light? How about one of these? We just did that, right? Town A has, it would just be town A. Town A has a population of 1,000 with a continuous growth rate of 6%. But we did it double just now. Ta-da! And I am grabbing all these, so these are all from the assignments, right? Just in words. I've summarized the assignments. And what I'll do is I'll just grab from the assignment questions. The numbers change, right? They're all randomized, but you will have seen them. And what I can do is I can put together a practice version with these questions in MOM, and then you can just have these to work through.
You don't have a practice one yet, right?
No, I'm way behind. So that's why I want to give you practice problems, and that's going to be the quickest way to do that.
That was super helpful for my second half, but it was kind of not that practice midterm.
I know.
We did that, and that was good, and then first time I did it, and I looked at all the ones that sucked at, and I just went back to like all the practice, and I just did like a million of each one over and over and over, and then I redid that midterm.
Yeah.
Obviously, I've seen it before, but
yeah, but I mean, it's still, yeah, still works.
But then I can like go through, and then I knew all the steps that I could, so I could write those down. I was doing it, and then I was seeing a question like.
Yeah, I don't like to do that. It's kind of how I was raised academically. It's like, no, if you know all these things, then you're good. That's all I want.
I really like the practice midterm because it kind of summarizes everything.
Yeah.
This you can always go over and like find the details.
Totally. It is on my to-do list today, but I wanted to do this because I obviously haven't made it yet. So it's I'm behind and I apologize. But now you know what's on the test. And I'll make a practice test of these.
Get the quick list of that, or
Yes, I can upload it right now. Let's see if I can. Math 139, no. Desktop, okay, let's see if I can drag and drop from here. Kind of experimental here. Okay. Looks like it's sort of thinking about it. I guess I can stop the recording, and I just realized I haven't been checking in with Steph. Sorry. 2 chats. Okay, I'm gonna stop the recording here.